Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. We have been discussing an interesting topic, which is CC cross-coupling reactions. These are palladium based cross-coupling reactions, and one of the famous recent reactions to have won the Nobel Prize, and also had made a elaborate journey from the confines of laboratory to the large scale industrial usage. So this cross-coupling reaction has gained its prominence particularly because of several reasons. First and foremost is that in these palladium mediated cross-coupling reactions, that there is no possibility of forming the homocoupled product, only the 100% exclusive cross-coupled products are formed, and that palladium is tolerant to very many functional groups. As a result, these palladium mediated cross-coupling reactions has a large scope of substrate variation. Secondly, this palladium does not have any toxicity issues which may cripple the large scale usage of metal mediated catalytic reaction. And third, an important factor which goes in favor of palladium is that the palladium is way too cheaper, even though it is an expensive metal, but it is relatively or comparatively way too cheaper than the magic metals of catalysis like rhodium, iridium and platinum. So all of this has tilted the balance in favor of palladium mediated cross-coupling reactions, and it has really lived up to its promise, in the sense that it has shown tremendous utility in various facets of organic synthesis, where these reactions have been used extensively. We have dwelled upon these cross-coupling reactions in details in the previous lecture, and we are going to be talking about some more about it before we go to allylic alkylation reactions. Now, as was discussed in the last class, that palladium mediated cross-coupling reaction sort of proceeds with palladium 0, which is the active species, and even though the palladium 2 precursor is used, and this palladium 0 active species is formed from the palladium 2 plus active species in presence of some base like phosphine, which converts palladium 2 to palladium 0, which then enters the catalytic cycle. However, for certain reactions like olefin oxidation, palladium mediated reaction like olefin oxidation, dehydrogenative aryl coupling, oxidative carbonylation, the active species, required is palladium 2 plus. So this is kind of different from that in other cross-coupling reactions, where palladium 2 precursors gets converted to palladium 0, whereas in reactions like olefin oxidation, dehydrogenative aryl coupling or oxidative carbonylation, the active species required is actually palladium 2 plus, and that gets converted to palladium 0 during the part of the reaction, and this is achieved by putting a separate metal which will convert palladium 0 to palladium 2 as a part of this. And for example, in Walker reaction, copper 2 copper 1 redox couple is used to generate palladium 2 plus, which is used for this reaction. I am going to illustrate this with this beautiful example where this copper 1 copper 2 subtle plays a prominent role, and that can be seen over here. 2 Cu plus reacting with 2 H plus plus half O2 oxygen generating H2O and 2 Cu2 plus. Now, this 2 Cu2 plus would then oxidize palladium 0 precursor to give the active species plus 2 in the following way. Palladium 0 to palladium 2 plus, and then copper 2 would get reduced to copper 1, and palladium 0 would get oxidized to palladium 2, and then this palladium 2 would be the active species required in this catalytic cycle. So, what we see is that for palladium mediated cross coupling or palladium mediated CC bond forming reactions, there certain reactions require palladium 0 as the active species, like cross coupling reactions, and certain reactions require palladium 2 as the active species, and for those there is a additional copper 2 copper 1 couple is required, and these are mainly used for Walker reaction, oxygen olefin oxidation, dehydrogenative aryl coupling, or oxidative carbonylation reaction. So, we are going to be discussing all of these reaction in bit more detail, and to begin with, let me just talk about allylic alkylation reaction. Now, this allylic now CC coupling reactions, in this context it is worth noting that CC coupling reaction in alpha position is well studied, whereas coupling at allylic position is overlooked. Let me illustrate this with the following two examples. For example, for the compound this hydrogen getting converted to an alkyl group, this is called alpha carbonyl alkylation. Whereas allylic protons getting converted to an alkyl group is called allylic alkylation reaction. So, this allylic alkylation reaction is sort of less studied to that extent, and we are going to start looking at this allylic alkylation reaction, where the alpha position of the allyl group, this hydrogen gets replaced by an R, and we are going to proceed by looking at the mechanism in which this reaction works. Now, to begin with, a palladium 0 species like PDL4 loses 2L to give the coordinatively unsaturated PDL2, which reacts with allyl halide in a step which is called oxidative addition. To give the oxidatively added product now. This oxidatively added product, where X is OAC acetate and L is PPH3, then oxidative added product then undergo a sigma pi type rearrangement of the type shown over here to give PD allyl PD L plus X minus. So, over here this sigma bonded palladium allele has become eta 3 bound pi bonded allele ligand, and this X has dissociated to become a non coordinating counter ion. The step 3 then involves addition of nucleophile which goes and attacks with the generation of the substituted product plus X minus along with regeneration of L2, which then enters the catalytic cycle. So, overall the reaction is such that this X moiety over here is replaced by this nucleophile Nu, and at the allylic position the way it is shown. So, this is a nice reaction, and that this also proceeds by 3 step. One involves this oxidative addition followed by sigma pi rearrangement and followed by the nucleophilic attack, resulting in formation of this allylic position getting the nucleophile, and along with the regeneration of palladium 0 species. Now, this nucleophile Now, it is important to look into the steps of this reaction, and this nucleophile prepare to attack from the less hindered side, and that is very nicely elucidated in case of cyclic substrates. So, stereochemical course of the reaction. Is best demonstrated with a cyclic substrate, and this we are going to show it for this set of cyclic substrates where this is schematically shown as R X M and minus X M equals coordinatively unsaturated complex fragment, natively unsaturated complex fragment, example PD PR 3 whole 2, then that undergoes attack from a nucleophile. So, this reaction attacks the X leaves, giving rise to this allylic metal complex X leaves, X minus leaves, giving rise to this allylic metal complex of the type this, and this may be illustrated by now to this. When a nucleophile which is a soft nucleophile attacks, then attacks happen from the less hindered side, giving rise to this compound which is Nu R, and that eliminates L and M to give this compound Nu R. So, what is interesting over here, if one compares with the initial Rx structure, that this is net retention of stereochemistry. Now, in case of hard nucleophile, when Nu is hard, then hard nucleophile attacks at the metal and a different reaction proceeds. Now, in this case, the metal stays bound to Nu, and then the nucleophile now attacks from the bottom part of the ring, resulting in the nucleophilic addition to the ring, which is Nu R M, and this eventually will lose M to give the corresponding compound which is this. And if one were to compare the stereochemistry of Rx with our nucleophile, this is net inversion of stereochemistry. And so, this is a interesting example where one can see that the stereochemical course of the reaction in which the attack will commence depends on what kind of nucleophile that one uses. And what is seen that in case of soft nucleophile, the attack happens for the from the extra side, from the further side, and as a result of which net retention of stereochemistry is observed, and this is shown in the blue by the blue arrows, or the pathway depicted by the blue arrows, and this proceeds in case of the soft nucleophile. However, the scenario is different when the nucleophile is a hard nucleophile, and in this case the hard nucleophile, instead of attacking at the alpha allylic position, attacks the metal and first binds to the metal, and then the metal bound nucleophile does one additional step in which the nucleophile attacks from the bottom of the from the endo side, resulting in the net inversion of stereochemistry from its starting point. So, this is a beautiful example which elucidates or explains the kind of stereochemistry that is observed and which is dependent on the type of nucleophiles added. Now, we are going to also look at another interesting form of this allylic alkylation, and this is asymmetric allylic alkylation. And in this case, there is this two compound, one is as shown over here, OAC reacting with the lactone substituted and it uses a big chiral catalyst shown over here. PH2 PH2 and both of these bound to palladium base and dissolved. Now this gives to this allylic alkylation product hydrogen pH R. So, diastereomeric carbon, which after workup would give the following amino acid R equals methyl and 90% yield and 99% EE. So, this is a very useful method in generating this amino acid containing a cyclohexyl group, and before this final workup the diastereomeric ratio that was observed as for R equals methyl, this to ratio was 8.7 is to 1 for these two chiral atom, or when R becomes isopropyl this even becomes 19 is to 1. So, this is a demonstration of how the influence of R can till the formation of the product favor formation of one diastereomer over the other, and how allylic alkylation has been exploited by using this chiral catalyst. So, with this I would like to come to conclusion of today's lecture. Today we had started by looking at the various kind of catalytic cycles to begin with, and what we had seen that in the most commonly observed palladium cross coupling reaction, the catalytic cycle initiates with the active species being palladium 0, whereas in certain other reactions like olefin oxidation as well as dehydrogenative aryl coupling or oxidative carbonylation, palladium 2 is the active species, and that has been achieved by coupling it to a shuttle, a copper 2 copper 1 shuttle in presence of air, in which dioxygen is converted to water. We had then moved on to look into allylic alkylation reactions, and despite alpha alkylation has been quite studied, allylic alkylation remains kind of less explored, and what we see that this allylic alkylation reactions proceeds in 3 steps. The first obvious of course is a oxidative addition sigma pi rearrangement, followed by the elimination nucleophilic attack giving to the elimination of the alkylated product, and then the regeneration of the palladium 0 species. What we had discussed further is that the stereochemistry of this allylic alkylation reaction is best illustrated for cyclic substrates, and for which we had seen that if the nucleophile is soft, then the attack at the allylic position happens from the exo side, resulting in the net retention of configuration, whereas for hard nucleophiles, the nucleophile first go and attack the metal center and then carry out an endo attack, resulting in net inversion of stereochemistry. Lastly, we had also looked into one example of asymmetric allylic alkylation, and what we had seen that this is quite an effective and useful method for preparing chiral amino acids with high yields and high enantioselectivity, and also we saw that for an intermediate species before workup, one can tilt it to its favor by increasing the bulk on going from R equals methyl to R equals isopropyl, and the diastereomeric ratio changes from 1:9 to 1:19. That is almost double. So, with that I would like to conclude today's lecture. Now we are going to be taking up another very interesting award, this Nobel Prize award winning cross coupling reaction, the Heck reaction in particular, in the next class, and that will be taken up in the next class. And I thank you for being with me in this class, and I look forward to take up Heck coupling in the next class in much more detail. Till then, goodbye and thank you.